Hi, my name is Dr. Barry Flannery. I'm the founder and CEO here at Xerotech. Welcome to XD Tech Talks. Today we're going to talk about battery fire safety and what happens if a lithium-ion battery thermally runs away. So let's get started. So lithium-ion battery fires, thermal runaways, and the many other terms that are used to describe them is an incredibly controversial and emotive topic in the electrification space today. It's what the most average person on the street might ask you a question or have some preconceptions on. People think, lithium-ion batteries, do they go on fire? What do you do? Is this a safe technology? Speaking from someone that designs and builds these systems, I think you've got to go back to a very fundamental question first before you even talk about battery fire safety. When it comes to fire safety or lithium-ion batteries, you need to first begin to understand what is a battery? What is a fuel tank? What are all the existing technologies today? Whether it's fuel, batteries, or any other source of energy, it is exactly that. It is a source of energy. Energy can be converted into heat, flame, fire, given the right conditions, or more importantly, given the wrong conditions. So the important thing to look at here is not, can a battery go on fire? Of course it can. Every battery can go on fire. Every chemistry can go on fire. And even the definition of what we mean by a fire, it may not be a flaming fire. It could be an electrically induced fire. There could be many different factors. And the point is to not look at, well, that goes on fire, so we can't use it, it's not safe. You must look through the context of, what do we use today? We don't even consider, can diesel or petrol go on fire? Of course it can. It's an extremely energy dense liquid, 10 times more dense than batteries or 20 times more dense than batteries, and it's a liquid. And it can also go on fire with a match in a fraction of a second. So both technologies present risks. They need design considerations of how to use them safely and effectively. We have built an entire economy and industry around an extremely energy dense, extremely flammable, arguably extremely dangerous fuel. In the future, we're going to build our economy around a different type of energy source, a different type of fuel, a lithium-ion battery. And it's got its own unique attributes, some of which are very similar to petrol and diesel-fired vehicles, and some of which are quite different. And that's what we're going to talk about today, is how batteries fail, how they're different to fuel-based systems, and how you can mitigate those, and to really cut through a lot of the misconceptions and downright dangerous misinformation on the market on what to do. So if we're to talk about today's most common fuels used in industrial markets, that's diesel. Diesel has an energy content of around 13,000 watt-hours per kilogram. It's a fantastic fuel. Diesel is one of the most incredible substances in the world today because of this incredible energy density. The very best lithium-ion batteries that exist today at a cell level, so not even accounting for all of the weight of the battery and everything else around it, is around 250 watt-hours per kilogram. This is an order of magnitude difference in energy content. It's huge. It's nearly 50 times lower than what we get out of diesel fuel today. That's the first most important thing when we think about fire safety, is that the energy density of diesel fuel versus batteries is dramatic. So that means that if something goes wrong with a tank of diesel, it's going to create a much larger thermal event, thermal incident, than an equivalent amount with a battery pack. Some of the big misconceptions with battery packs is that they're very difficult to combat the fire, very difficult to put them out. And I'm going to speak in detail as to why that is. And in some cases it can be true if you deal with the fire in the wrong way. So if we're just to use a simple example here of an industrial machine that's got a 100-liter fuel tank, that's approximately 80 kilograms of diesel. So multiplying 80 kilograms of diesel times 13,000 watt-hours means that this system, this 100-liter tank of diesel, has basically got 1 megawatt hour of thermal energy. That is a huge amount of energy in that system in comparison to what a battery could carry. So a battery for an electric vehicle might only have, it could be on a Tesla, it might be 600 kilograms or a 70 kilowatt hour battery. So when you take that 600 kilograms and multiply it by this value of 0.25, you end up with 150 kilowatt hours. It's an order of magnitude lower amount of energy in a battery compared to the fuel tanks that are in every vehicle you deal with today. The difference between the diesel fuel and the battery is that the firefighting methodology we use for diesel is very different. So by suppressing a diesel fire, by covering it in a foam or blocking oxygen to it, it's able to put this fire out and maintain it in a completely extinguished state. The difference with a battery is that in some cases it can be self-oxidizing. It's able to generate its own fuel internally and continue to burn, but the most overlooked piece is that it's electrical energy. There is electrical energy stored inside of this battery cell, and that means that you've got multiple modes of thermal runaway, multiple modes of fire generation, multiple modes of heat generation. So if we're to look through what actually happens in a lithium-ion battery to cause it to go on fire, it's quite a nuanced set of things that happen. So inside of a cylindrical battery cell, as we've shown in previous videos, it's basically something called a jelly roll. It's basically a plus and a minus, and they're separated in a flat sheet. And then this flat sheet, in the case of this cylindrical cell, is wound up into a single loop. So that will enable you to have a functioning battery. This is containing electrical energy, and then similarly, this red separator is a plastic. It's a little polyethylene separator material. So a plastic can burn. It's like a hydrocarbon. You've also got electrolyte in there, a small volume of liquid that's quite combustible. It's almost like an organic liquid, like diesel, but only a small few droplets of it. So within the battery cell itself, there are things that burn. It's like oil. It's like there's almost a small bit of oil inside of the can before you even consider all of the electrical energy. So the electrical energy is the second piece here, is that if this battery cell were to catch fire and you're able to break down the separator and cause these two sides to touch, you're going to create an electrical short circuit. An electrical short circuit can generate a lot of heat because the current flows through resistive heating build up temperature very, very quickly. So you can get multiple things taking place at once. You can get electrical shorting generating heat. So it won't generate a fire, it will generate heat and burning. That heat and burning will cause the separator and the electrolyte to catch fire, which then causes venting and gas generation, which causes more separator to fail and more electrical energy to be released. So when all of these factors come together, you can and do get thermal runaway. You do get venting of battery cells and fire. There's a lot of different technologies on the market today to try and reduce this. And some of the things to consider is that even within this plus and minus, or your anode and your cathode, the materials that are used there, they have different stabilities. They're chemical compounds. If they get above a certain temperature, they break down, they decompose into other materials that are often flammable. So when we talk about different chemistries that are, this is very safe, LFP doesn't go on fire, LTO, you can put a nail through it. These chemistries, these cathode chemistries, have different characteristics. They might have a much higher thermal stability before the cathode or some of the other components break down, which means they need to reach a higher temperature here before they burn. The electrolytes they use might be less flammable. In fact, you can get non-flammable electrolytes. The separators that are used could be different. They might be inorganic electrolytes, inorganic separators. They might be ceramic separators that simply don't burn. So by tweaking all the aspects of these battery cells, you're able to change their behavior in thermal runaway and fire. But the thing is, with all of these battery cells, they still have electrical energy. They can all fundamentally create electrical heating by releasing their energy. certain cells you might have seen that you can drive nails through them. That's because the current conductivity through the cells is not so high compared to others. They can't release the energy quick enough to generate that high heating effect and burn the other materials. But I have to be absolutely clear, given the right conditions, you can make any chemistry burn, thermally run away, or create a fire event. So understanding these two different effects within inside of a battery, there is the chemical, burning, there's electrical. The second one is the big difference between diesel. So when we talk about lithium-ion batteries versus diesel, diesel's got chemical burning, but it has no electrical heating. The electrical heating is the source of most of the confusion on the market today. It's the source of most of the very interesting news stories and firefighting mistakes, is that electrical heating and the fact that the energy is always there, always on, can lead to a very key behavior that needs to be mitigated. And that key behavior is reignition. So the important thing to think about here in my scenario of, if you're able to cause chemical burning of the battery, you can extinguish that burning. You can put it out with any standard conventional method. You can put water on it. You can block the oxygen, assuming it's not self-oxidizing, and the battery cell will go out. The fire will stop, no different to a diesel fire. The thing that you possibly have not achieved is there's probably still electrical energy inside of this battery cell. If you still have electrical energy inside of the battery cell, and you've still got a compromised heating path, you've put out the chemical burning fire, but the electricity is still flowing, creating heat effects, and that might be enough to reignite a chemical fire either seconds later, minutes later, hours later, years later, potentially, in a very latent defect. So that's something that you've got to be careful of with battery fires, is that you need a form of permanent suppression to ensure that these systems can be made safe. So that's what we're going to talk about next, is first responders, what you should do, how you tackle battery fires. So if you were to come across a vehicle, a battery, a system, this is based on the best practices that we do here at Xerotech. So there's a lot of information out there publicly. There's a lot of different scenarios, but what we advise our customers to do, and the Xerotech philosophy, is based on real fires, real testing that we have physically done ourselves. I personally have fought multiple lithium-ion battery fires during design, development, and intentional abuse tests. So these are methods that we have directly seen to work and be effective. And the real simple case of how you deal with every battery fire, we have one rule: put it under water. This is the simplest, most effective way to deal with a lithium-ion battery fire. In every case, irrespective of chemistry, irrespective of everything else, this is the permanent solution to make a system safe. Everything else you do combating a fire should lead to this end point. The end point for combating a battery fire is submerge it underwater. Get the system underwater. That will put out the battery fire. That will suppress it. It will make it safe for days, weeks. And these are some of the challenges you have with many of the solutions that are being sold on the market today are fancy fire extinguishing agents, other strategies and things like that. That can usually deal with the early minutes or hours of a fire. The problem is that with real lithium-ion battery fires, at some point it ends, at some point it stops, at some point everybody goes home. That's where the real danger happens, is when everybody's gone home and something is left somewhere. What happens in the middle of the night or a week later when nobody's there? You need permanent suppression, permanent solution to dealing with the fire. And that is the simplest, cheapest, most available solution in the field is fully submerge it underwater. All of the other approaches like fancy fire extinguishing agents, blankets, everything else, these are to buy you time. These are to make the incident less severe so that you can ultimately get it underwater, get it out of a vehicle, put the vehicle underwater, whatever the solution is. But the end point is to get there. What should you use on a lithium-ion battery fire? Should you be using special fire extinguishers designed for lithium metal fires, or fancy salts and fancy suppression systems? Again, based on Xerotech's experience and all the fires that we combat and our recommendations, we keep it really simple. And that answer is water. Water is the most effective solution for knocking down a lithium-ion battery fire. Some people might be concerned about, well, you can't put water on electrical components, you'll get electrocuted. And in most cases, that's very valid advice. But batteries are fundamentally different. A battery is what's called floating. It's electrically floating. The only way you can get electrocuted from a battery is you've got to touch from plus to minus. You've got to join these two loops together. So if you've got a fire hose, you would have to somehow create a loop where you're in the middle of it and join these two things together. That is incredibly hard to do for a floating battery system. The reason you don't spray water onto an electrical panel is that you don't need to connect the second half of the loop. Half of the system is already grounded. So you're standing here on the ground. And that means that if you've got an electrical panel here, it's got one side that's going off doing something and the other one's connected to the ground. So if you spray water onto that electrical panel, you're creating the loop and you're in the middle of it. So that's why you never do this with a ground-tied system or a system that's not floating. With a battery, it's very hard to achieve that. So in this case here, if you spray water on the battery, you will create a joining of the circuit, but you're not going to be a part of that circuit. It's going to be inside of the battery box. It'll be internally shorting and dissipating its energy. And that's actually part of the mitigation strategy for putting it under water. You leave it under water. So if we're to come back to a practical solution of what you do and how you put out a fire, is we would recommend as a general rule, if your battery box is a certain size, put it in a volume of water that's at least more than 3x the size of that. And there's a number of different reasons for this, is that if you have it in a small pool of water, there's not enough thermal mass in that water to keep the fire quenched down. So you want to have greater than 3x the size of the pack, and you need to think about practical solutions of how you'll do this, especially in a field application. And oftentimes these are achieved with metal containers. Waste refuse skips are some of the most effective solutions that we would recommend for customers, early integrators, is that have a standard metal refuse bin, large skip, put the pack in it and flood the skip. Other effective solutions are large roll-on, roll-off skips that can be lined with a tarp to basically create a swimming pool and putting the packs inside of it. By spraying water on the pack, if it's venting or flaming or whatever the solution might be, this will knock down the flames, but it's likely going to be temporary. You have a high risk of reignition by just externally dousing a pack with water. But it'll buy you enough time to get it somewhere more safe. So that's the second piece with lithium-ion battery fires. One of the most important things is early intervention. The worst thing you can do is let it to burn more and more and more. So if there's an opportunity that this is a recoverable situation, you want early intervention. This is incredibly important. Within batteries, we're very lucky that the fuel is not a liquid fuel in one tank. A diesel tank, like we spoke about, an 80-litre, 100-litre diesel tank with 1 megawatt hour of energy, it's one volume of diesel. If it goes up in one place, it's very hard to segregate it. If a battery is designed well, you've got lots of little diesel tanks. For example, in a 1 megawatt hour system, that's probably 10, 20, 30, 40,000 battery cells, individual cells. So that 1 megawatt hour is divided by 40,000 times. So that means that if you can intervene early, you can stop the domino chain reaction within the pack. But again, spraying water on it will only eliminate the chemical burning. It is unlikely to stop the electrical shorting, which can reinitiate chemical burning. And the problem here is that water does in fact promote further short circuits. So the water is in some cases going to make things ultimately worse for a short period of time. So water is what you do at the final point. You know that you're committed. This pack is going to be end of life. So you're dousing it with water with the intention of taking it out of the system, putting it into a skip of water. Some other considerations for practical firefighting of battery systems, particularly in large field vehicles, is back to our fundamental rule of thumb of get it underwater. We ideally want to take the white box out of the vehicle, put it in a skip of water, but for some systems that's not possible. You could have a massive system with 30 battery packs. How are you going to do it in that case? So some battery systems, like ours, we've designed in abilities to spray water into the pack. Can we flood the pack internally? So if you flood the internals of the pack, that will be an effective way of maintaining the pack outside of chemical burning. It will still be electrically shorting, and there are some considerations you need to worry about there. So it is not a good idea to have a very small amount of water in an active electrically induced chemical fire, because the water can evaporate away, build up steam, and you'll lose that cooling. So if you're going to inject water into the battery housing, you need to be able to refresh and flush the water through it. So if you design your system that you can put a cooling hose or a water hose onto that system and flood the pack, this is the equivalent of putting it in a large tank of water. That will enable you to make this system safe until it can be taken out of the system after a period of time. As a general rule of thumb, it varies from case to case and it's not always perfect, but leaving a battery system underwater for 1 week is usually a good, safe measure before you want to take it out and decide what to do with it next, like recycling or ultimate end-of-life destruction of the system. There's a lot of other tricks that you can consider if you're trying to move failed battery systems. That's another area that's not well spoken about in the market. Some of the recommendations we have is submerge a pack in a skip of water to make it safe. And then afterwards, when this pack needs to be transferred, we recommend putting them in sealed plastic, heavy-duty tarp bags so that they can be underneath water while they're being transported to the final end-of-life location. So again, keeping that chain underwater provides the maximum level of safety, reducing the risk. And the reason water is so effective compared to any other solution on the market is the thermal mass of water is probably twice as good or strong as any other material known to man. Water is the most effective firefighting material that exists, and it's widely available, well known. We strongly recommend the use of water in combating battery fires. One of the other considerations with lithium-ion batteries and a watch out is when batteries fail, they don't typically start by catching fire and burning. They typically vent. And what we mean by venting is they vent a hot gas. And what that is the battery cells start to decompose. The electricity inside of them is cooking the liquid electrolyte, turning it into a combustible vapor. A very dangerous situation that you can create when you don't understand about how to combat battery fires is taking a battery and putting it into a sealed compartment. This is not a good idea. There's a big difference between putting a battery in a sealed compartment and putting it underwater. The water will knock down the thermal runaway. It will stop the gas generation. It will stop the fire. It will cool down the heat. When you place a battery in a sealed compartment, and we've seen this several times in container situations, if a battery is in a container and it's venting, you build up gas, and this gas can be combustible. The risk you have here is if you achieve in your gas volume, say in a shipping container, and you've got an individual pack, as this starts to engulf the whole container in gas and build up a certain concentration level, you build up quite typically a lot of hydrogen inside in this space. And if you have a spark ignition of that hydrogen, you can get a temporary ATEX or explosion hazard. It'll be a sudden pop, hydrogen bubble pop, that will in some cases overpressurize the container. It could swing open the doors of the container or pop the lid of the battery box. It's very important that if a system is failing, you want to make sure it's in open vented air. So as part of the chain of how you deal with these issues, you want to get it outside if this is possible. For example, in a production environment, you want it in an outside area. You want to be keeping the smoke, gas, and fire generation down. So water on the pack. And then the final piece is submerge. We strongly recommend never ever to store failed battery packs in sealed enclosures or sealed containers. The safest solution is to leave it permanently submerged and recycle it, or else leave it in open air and cover it with some sort of fire blanket or protective covering, but not something that can create a pressure vessel scenario. So to summarize, you've got two major scenarios that you'll encounter battery fires. You could encounter a battery fire in a production type environment. If something goes wrong, if a battery pack is dropped on the production line or a forklift operator drives through it or something like that. And the second one is in the field. In a production environment, the solution is generally very straightforward. Get it outside, get it underwater, use water as a containment. In a field application, it varies very widely on what to do. Typically, if it's a smaller size vehicle where the battery is just one battery in a vehicle, you may want to douse the battery with water so that it can potentially be removed from the vehicle, contained enough to make safe. Potentially you can partially submerge a portion of the vehicle if this is practical. For larger systems, depending on how the OEM integrates it and designs it, you might design in cooling ports that you can flood the pack for first responders, if that's the most sensible thing to do. So we've talked quite a lot about how to combat a lithium-ion battery fire, but one of the most important things to look at, particularly for Xerotech battery systems, but not just ours, is there's a lot of interesting things that these battery packs can enable, particularly in markets that experience very adverse or very abusive conditions. One of the big advantages of battery packs is the small units of energy. These small units of energy mean that these systems can oftentimes withstand a high degree of damage and still be somewhat operational. And this is very interesting for some markets. So in those markets, when you've got a fire in the system, for example, with a Xerotech battery system, there's a very high likelihood we're going to passively suppress that fire and you can maintain operation. But even if it is a runaway event and it continues to happen, this is likely happening over a period of time. It could be minutes, it could be hours, it could be even longer than that. That gives the user a huge amount of safety benefit to exit the vehicle, to complete their mission, to continue the use case, to put the whole system into a safer mode of operation. That's one of the things that's overlooked on battery systems. And while there's a lot of fear in the general media today about batteries and battery fires, the actual evidence when compared against internal combustion vehicles is pretty incredible. The incidence of fire, first of all, is orders of magnitude lower. It's like 1% of the incidence compared to combustion vehicles. And that makes sense. It's not a case of the systems being fundamentally safer, which they are. It's that the energy content is way smaller. There's much less energy in lithium-ion battery vehicles compared to diesel vehicles. The energy is compartmentalized. It's much smaller. The fear factor and the confusion has come from the inappropriate methods of combating fires. So the reignition risks, the inappropriate ways of spraying water on the wrong places. So as we learn more, as first responders and others become more trained in how to deal with these, we're going to see a much safer system deployed in the market as we go forward. So how do lithium-ion batteries start burning? How do they go on fire in the first place? There's a number of different mechanisms for this and how it could happen. And the first thing to say is it's generally pretty rare. The incident rate is a lot lower than any conventional technology. And that's an important thing as a technologist, is that if there's a technology that's dramatically more safer than the incumbent technology, it's very important to introduce them because it's saving lives. So while some of the events that can happen can be sensational, it's not the right solution to not do it. If it is safer, we must and we should use it. But how do these things actually start in the first place? You can generally categorize it into two categories. You've got internal and external. The internal one, the mechanisms are always the same. You've got to generate heat. If you generate heat either through chemical methods or electrical methods, that's going to ultimately lead to fire given the right conditions. So internally generated faults are always initiated electrically because there's no way to internally generate chemical fire. So internal faults could be manufacturing defects, which are incredibly rare and uncommon. The largest battery manufacturer in the world, a major Chinese battery manufacturer, just recently released a large data study of their cell quality. They've estimated that their failure rate of cells is 1 in a billion cells. That is an incredible number of current modern quality standards. So internal faults are incredibly rare within the battery cell. But how it could happen is if you have a defect here creating a small internal electrical short circuit that then causes heating, that causes burning, that starts to burn the chemical fuel inside of the cell, that can then lead to fire. So we try and mitigate these things through having very high and rigorous standards of cell manufacturing quality. We do extensive things as us, a battery manufacturer, would do quality checks to make sure the cells are good. And this is after the cell supplier has done that. Then afterwards, we wrap a lot of safety systems around it to plan for the worst. What if it does go on fire? That's, in our case, we have foam suppression and active suppression and many other features to knock these things down. So the internal faults are incredibly rare. You may have other internal faults within a battery pack that it's not actually a battery related fire. It might be an electrical fire. You can see there's a lot of other electrical components in this system. There's bus bars, there's bonds and connections. Anywhere you're moving electrical energy or electricity, there is the risk of creating heat, creating fire, creating thermal events. And that's separate to the battery. Even if you just had the electrical grid, electrical panels can go on fire as well. It's a different type of behavior. The difference with batteries is you can't switch them off. And that's one of the things you've got to account for with some of the methods we spoke about previously. The external events, there are many of them that can trigger this. But again, the fundamental thing you need to consider is a battery will go on fire if you electrically release its energy through a short circuit or you burn the chemical fuel in the cell. So how do you do this externally? If you overheat the cell, you'll cause decomposition of the cathode and other pieces of the battery, breakdown, thermal runaway, melting of the separator, electrically induced short circuit. And even if you don't get an electrical short circuit, eventually if you reach a temperature where the liquid inside of this cell or the hydrocarbons burn, it'll just burn like diesel, small amounts of diesel in the cell. But if you drive a nail through it, what you're doing is you're shorting out the electrical energy. You're causing that electrical heating to trigger a chemical burning effect. But it varies from chemistry to chemistry. Sometimes they can't generate enough heat. Sometimes the internals have a high initiation temperature that they can't burn so easily. So some will be more stable than others. You have to pick and choose your chemistry depending on your safety needs and safety requirements. There are other factors, not just penetration, but crushing the cells. It's the same behavior again, creating electrical short circuit, leading to burning. And this burning can then lead to a larger thermal runaway and the release of energy in other cells. In large complex battery systems, the thermal runaway chain of events can be quite complicated. There can be small initiators that lead to other effects, and you're switching from chemical burning to electrical burning back to chemical burning. It's a complex failure mode on how it ultimately occurs. But the mitigation is always the same: water and submersion. So very simply on the Xerotech design, we've put a lot of thought into thermal runaway prevention, thermal propagation prevention. So really what we're looking at in our design here is we like small units of energy. I like to have a lot of little fuel tanks as opposed to one big one, because if you have an event with a single cell, you want that to be a small amount of energy. It's a lot more manageable, it's containable. So within our module design, you'll see small units of energy. The next piece you'll see is a structural fire retardant foam that separates every single cell from every other cell. So that's incredibly important. It means that if you have an event on a cell, it's probably going to fully stop at just one cell, or it's going to really slow it down over a period of tens of minutes, if not hours. The second piece that we do that's entirely unique to Xerotech is our cooling system is a plastic duct, a really thin plastic duct filled with coolant, water and antifreeze. This duct is designed to fail. It's frangible. It's designed to fail like a fuse if a cell propagates or if a cell thermally runs away. That will cause localized flooding directly onto the cell in question. The water doesn't go much further than this cell because it's still encapsulated by foam and it doesn't have very good flowability through the module. This would still be an end-of-life event for us, although you may have a survivability requirement that you want to maintain operation for a period of time. But that enables us to have a very, very high degree of safety from both internal events, but also external events like ballistic issues or external bulk penetration, bulk crush. This holistic approach to safety is really important. And that's one of the big challenges on the market today is most customers, most people on the market think safety stops with the choice of cathode chemistry. Cathode chemistry, for one, is only one of 4 things that actually goes on in most commercial cells today. You've got to then look at the module level. You've got to look at the pack level. You've got to look at the active electronic control level. Safety is an onion layer concept, that there is layer after layer after layer of safety, beginning with cell supplier safety and raw materials, all the way up to very advanced active electronic protection. So lithium-ion battery fires can happen, they do happen, and they will continue to happen as we have more and more electric vehicles on the road in the future. But the key thing is, this is just a new engineering risk. It's something we have to deal with. It's something we have to engineer. And the key thing is, it is safer than conventional technology, substantially so. So using batteries is ultimately a good choice from a safety perspective, provided that you take the right precautions and you know what to do in the extremely unlikely event that something goes wrong. I hope you found this interesting, and thanks a lot for watching.